Okay, so now comes the fun part, the live interpretive walk or interpretive dance of evolution. And so for that, I need to step back into the rest of my studio here and explain that I want to use the front of this room by way of illustrating how you're going to have allele frequency change within populations. So we're trying to bring together all of these evolutionary mechanisms and concepts. So we're going to talk about Mendelian variation, focus on that, and we're going to talk about one gene with two alleles. So you have to imagine that the front of this room is representing for you allele frequency. So on one side of the room you have one of the two alleles is completely fixed, and on the other side of the room the other allele is completely fixed. And then my position represents the frequency in a given population or gene pool. So if I'm standing right here in my professor clothes and my professor pipe, I am at 50, I'm representing a population with an allele frequency of 50% of one allele and 50% of the other allele. If I'm over here, then I'm representing a population that has 100% of one of the alleles, like big A, and 0% of the other allele, little a. But if I'm over here, I have the other set of allele frequencies. So over here I think I'm 100% little a, meaning that I'm also 0% big A. So as I, as a population, move across here, I'm representing changes in the frequency of those two alleles within that population. So that's the setup. Now, in order to demonstrate this, I have to change my persona here from the Oxford-style professor to basically a drunk. Okay, so you have to imagine that I'm a drunk coming out of a bar in Montreal, or I've talked a lot about Alaska, so I'm coming out of a bar in Alaska. Okay, and you know, on the way out, I stole a bottle of some fine alcohol. This was all I had here. Absolute vodka. It's pretty hideous thing, but I hope it gives you the point. So I come out of the bar like this, and that means that the population, me, the drunk, is starting at 50% allele frequency of each of the two things. Then time is represented by each step. So this is time 0 coming out of the bar. This is time unit 1 coming out of the bar like this. Time unit 2 would be one more step. Now, I can't walk through the middle of this room to show you, so instead you have to imagine I'll take steps backwards or forwards. But each time, sideways. But each time I take a step, that represents one time step, like one generation. Okay, so I come out of the bar, I'm a drunk, right? I have a little swig of my alcohol just to get in the mood here. I hate vodka. I'm going to put that down so I don't break it. Okay, so I come out, I'm drunk. Now, what does a drunk do? A drunk staggers around, right? So I'm going to stagger. That's one step. I'm going to stagger over here, then I'm going to stagger over there. And if you remember, time is like a conveyor belt now moving under me, so I'm going to stagger like this. And that represents time. So the drunk is staggering around. That represents genetic drift because it's random. If the road is flat, I'm as likely to stagger this way and back as I am to stagger over here, like this. Okay? So random genetic drift is like a drunk staggering down the road. With the two sides of the road are the opposing allele frequencies. Now you can also imagine that a big population, like a really heavy drunk, is going to stagger less each generation than a really live drunk who's going to stagger all around, which is again illustrating the idea that a big population will show much slower changes in response to genetic drift than will a small population, which was also illustrated by the coin flipping in that Rosencrantz and Guildenstern movie. Okay, so genetic drift is causing me to stagger around like this through time as I come out of the bar, And then eventually what's going to happen is as I'm staggering around, I'm going to fall in the ditch over here or get stuck to the wall. Now, if I fall into the ditch, I'm going to stay there because I've lost all of the one allele and I'm 100% fixed for the other allele. So here, I'm 100% little a. Now, I could have staggered over here because it's completely random if I started in the middle. And in this case, I'd represent a population that was completely fixed for the big A allele. Now I'm going to stay here, and I'm going to be stuck in the ditch, stuck to the wall, and time is passing by, the wall is moving past me, the conveyor belt underneath me, I'm just going to stay here forever. Unless a mutation occurs, which gives me little a again. So that mutation is like a good Samaritan that picks me up out of the ditch and starts me off again. Or a bump coming down the wall through time, and that bumps me off the wall again. Now that mutation is just occurring in one individual and its children, so it's not going to move me far from the wall. Which means as I stagger again, now I have genetic variation, I'm most likely going to end up in this ditch again. Because I'm closest to it, and I'm staggering at random. It is possible, of course, that I could theoretically stagger all the way over here and end up in this ditch, but it's much less likely because the mutation just brought me a little bit up. So there's a small frequency of that new allele when it starts off via mutation. Okay, so that's genetic drift. I'm staggering around a drunk. Now, you can layer other evolutionary mechanisms on top of this. That was genetic drift and mutation. You can layer other mechanisms on top of this, like natural selection. So natural selection says that one or the other allele is favored. You can envision that as a bit of a slope in the road. So if the road is sloping this way, it suggests that that allele is favored. So the drunk comes out, he's staggering around, and sure, he's going to move back and forth a little bit at random, but really, the road is going to cause him to end up in this ditch. And he's going to stay in that ditch. Whereas if the road is tilted like this, time is moving along, he's staggering around, he's most likely going to end up in this ditch. Which is basically illustrating the point that when natural selection gets involved, it's most likely going to overwhelm genetic drift. So natural selection is going to win. You can have other forms of natural selection as well, like balancing selection, which would be a road like this, where you come out and you stagger around and you don't go too far in either direction. Because natural selection is favoring a balanced mixture of alleles in the population. Keep going with these metaphors, layering them on top, these mechanisms. You could have sexual selection. So you come out of the bar, you got your stolen body of hooch, you come out and you're staggering around and there's a lady of the night, for example, or a guy over there going, hey baby, want a party? Right? And so, you come out and you stagger over here. So sexual selection can also cause non-random changes in allele frequency depending on which allele is favored. And in the lecture, I talked about this opposition between natural and sexual selection. So you can imagine that the road is sloped like this because of natural selection. So you come out and you're most likely going to get this allele fixed over here. But maybe simultaneously there's someone over there going, hey, baby, want a party? And so, you don't get fixed by natural selection, you don't get fixed by sexual selection. Instead, you're stuck somewhere in the middle. Natural and sexual selection opposing each other. And then finally, you can think about genetic drift you can think about gene flow as two drunks coming out of the bar, holding hands or even better attached by a bungee cord. So the two drunks come out and they stagger around together, but they can't completely separate from each other because they're connected by a bungee cord. And that's gene flow. That's exchanging alleles between the two populations and keeping them together. Normally I illustrate that with my wife or my daughter. We come up and we hold hands and stagger around in front of the room, but I'm home alone today, so I can't do that. Okay, so that's the drunkard's walk metaphor or interpretive dance that tries to explain how the different evolutionary mechanisms can work in a conceptual fashion. And I will post a better version of this online
after the lecture.